Next week in class, we are going to be focusing on our first ways to solve systems of equations using matrices, specifically using elimination. So you guys have used elimination before in the past. It's one of your techniques that you can use along with substitution, but we're going to formalize it in terms of a matrix. So we already know that linear algebra provides a really convenient way for us to write a system of equations. We can write it in matrix form, or ax equals b. And we can solve it using linear algebra notation. So we're going to go ahead and that's the way where x equals a inverse times b. And we know how to do that in MATLAB. We know how to do that for 2x2 systems. We're going to expand that process this week and in the next coming weeks. Just some vocabulary. We have a homogeneous system, which is where we have a right-hand vector of zeros. That's what you're doing in your homework for next week, where you have your linear combination where C1 V1 plus C2 V2 plus C3 V3 equals 0, one of those types of scenarios. This is a homogeneous system because our B vector is zeros. Otherwise, we have non-homogeneous systems, and there's applications of both. And here we can see the table that shows us all the different ways that we can write our system equations. I did not include linear combinations in here, but we can have our original system. We can write it in AX equals B. And I showed you guys on Wednesday of this week that we can go ahead and just take out all of our unknowns, because in reality, it doesn't matter what they're called. All we care about are the values in A and the values in B, and we know that because that's all we type into MATLAB. So we can go ahead and take that out and write an augmented matrix where this side is our A values and this side is our B values, and we go ahead and denote the difference between those with that line there. So over here I have an example of this. So here I have an original system, 3x1 plus 2x2 minus x3 equals 6, two more equations. This is how we typically see our systems written out in problem statements. But we can go ahead and write it in form of ax equals b, where a contains all of my coefficients. So 3, -1, 1, 2, 2, 1, -1, -2, 3. And then my x. Here's my x, it's full of my letters, full of my unknowns. They can be called whatever in the system, x, y, z, a, b, c, z1, z2, z3, it doesn't matter. And then the constants from my right-hand side go in my b vector. So keep in mind, when you construct A, these values come from the same equation, these values come from the same equation, these values come from the same equation. And then these values are in front of the same unknown, these values are in front of the same unknown, and these values are in front of the same unknown. So make sure when you construct A, you're creating that grid of equations and unknowns. And then once again, we can take this out and we can go ahead and pull our A values here, our B values here, draw a line between them. And this is our augmented matrix. And this is where we're going to be spending a lot of our time solving systems, at least for this material, because here's where we're going to do a bunch of our elimination processes. And we'll step through what that looks like. So for each equation now, we can go ahead and think about each equation as a row in A. It can be viewed as the dot product of row I with my vector of unknowns. So if I take this row and the dot product with this, that will give me my original equation. Each row or each equation can be viewed graphically as a line. We know what that looks like in 2-dimensional space, 3-dimensional space. Above that, we get a bit uncertain in terms of what everything looks like. We can view everything as vectors as well. So each column in A can be viewed as a vector, graphically as a vector. Each row can be viewed as a vector. And then our matrix can also be viewed as a linear combination. We talked about this earlier this week, where the columns of A with the corresponding components of X. So this column in front of X1, this column in front of X2, this column in front of X3, etc. So there's lots of different ways we can view our system of equations.